Okay, so this will be recorded if you guys have to leave early, because I do have like full 2 hours of material planned. I don't know, we might get through it faster, but if you need to leave early, that's totally fine with me. Like I said, this will be recorded. So sounds like, unless anyone else has anything they want to have me start off the bat with going over, kind of I guess what we're going to do today is we're just going to go through exam 2. I'm going to go through some questions and then I'm going to review the material related to that questions. That way we test first, see what you know, and then we can kind of follow up with some material. But before I begin, does anyone have any particular questions that they need answered right at this very moment? Okay, perfect. Let's go ahead and get started. So my name is Ben. For those of you who maybe didn't meet me while I introduced myself, I'm going to have the chat down here because I pretty much never see it. So if I'm missing your chat, just yell into the microphone, and that's fine with me. Okay. So I hope everyone's got pen, paper out, something to write on. We're just kind of going to go through these. I'll give you guys about 30 seconds to go through it on your own. And then I'll just kind of go through the answer. Hey, does anyone have an answer yet? Just shout it out. I don't care if you raise your hands or
C.
water. Good job, guys. All right, perfect. So this one's pretty easy. I don't think I need to go over this one in too much detail. The one that has the hydrogen is the hydrogen bond donor. The one that has the oxygen, right, or the nitrogen or the fluorine is the hydrogen bond acceptor. So if it doesn't have the hydrogen in that bond, then it is the donor. Any questions on that? Okay, let's get going then. Which of the following choices below contains only functional groups that contain a carbonyl carbon? Come on in. B. Yeah, so it's B, right? And so to remind you guys, this is what a carbonyl carbon is. Okay. Alcohol. Right off the bat, we know it's not A because this is the OH group for an alcohol. C has alcohol as well. Amine, we know, is just this group, or I guess NR3. Doesn't necessarily have to be that, right? So we know it's not that one. And that's kind of just process of elimination there. I'll draw these all. So an aldehyde is this. Ketone is this. These are R groups. They don't have to be the same R group. Carboxylic acid is this. And amide is this. Okay. Memorize these. I'm sure y'all did in OChem, so just take some time to kind of go back over them, get them memorized. Anybody have any questions about this? Yes.
But N dash, is that an R3?
Yeah, this is an R3. It just means that it's 3. Yeah, it could be hydrogen, could be another carbon. Yeah. And it doesn't even necessarily have to be R3. It'd be like this. But the point is, the thing you're going to recognize with an amide is the carbonyl attached to the nitrogen. Make sense? Okay. All right, what's this one? Yeah, I kind of gave that one away, so that's pretty easy. Any questions about that? Okay. All right, so this one's just kind of a blunt memorization one. Let's see if you guys got it. Good job, right? Someone's been studying, right? Oh, yes.
Do you just, I mean, I'm sure it's the PowerPoint, I can just find it, but do you by chance have the chart?
Yeah.
Like bond association?
Yeah. Yeah, so these need to be memorized. This is from presentation 1. So if you guys haven't gone over the first slide presentation, it's worth reviewing because it is all pretty easy material, right? But you do need to know these numbers. This one's tested quite often. The bond lengths are tested. And kind of the key way that I like to memorize these that help me kind of think is that, okay, covalent's my strongest. And so it's going to be the biggest order of magnitude. And so it's 350, right? And so, yeah, 3,500, this would be something like an actual like molecule with lots of chains and stuff. But just memorize these, put them on flashcards. It's important to know that van der Waals is the shortest length. I know I missed this one on my exam because I thought covalent's the strongest, so it's going to be the shortest length, right? That's actually kind of not true because van der Waals, because they're so weak, they need a short interaction in order to actually do anything. If you're greater than 1 angstrom away, it's not going to be very helpful. And then covalent and hydrogen bonds are actually pretty similar. So most likely you might get a question about van der Waals interactions. Just remember those are the shortest bond length, and your electrostatic ones are the longest, which makes sense, right? Any questions? Yeah, sorry guys, this one's just blunt memorization. So I know there's a lot of questions about this number, and there's a lot of questions about this number if you feel like you can't memorize it all, but I would suggest memorizing it all. Which of the following characteristics of water contribute to the polarity of water molecules?
All of the above.
Yeah, good job, right? So let's draw a water molecule actually. Okay, so one thing that you have to notice is that, first of all, this is bent, right? That's something that you need to know. And it's bent because those electron clouds push down on the bond length. So it actually decreases this bond length from like 109 to something, I don't know, not important. That's just me guessing. I actually don't know the true numbers. But because of this shape, right, we have 2 hydrogen bond donors and we have a polar molecule. And so it's actually all the above, A, B, and C. The hydrogen oxygen bonds being polar allow it to donate hydrogens and also accept hydrogens. The tetrahedral electron domain kind of has to do with that bent molecular geometry. These kind of go hand in hand, right? Those empty orbitals allow for it to make that. Any questions on that? Okay, that one's kind of tricky. Might be worth reviewing your notes for that one. If you get to a question like this, one question you might ask yourself is like, well, water does have all those things and they all contribute, so it's probably all of them. Okay, chemical bonds. I'm just going to go through like a couple key ideas, in summary after kind of like a section of notes, right? So it takes energy to what? A bond. What requires energy? Break a bond, right? And energy is what when a bond is formed? Release, right? So the way that I remember that is my hands are atoms. I clap them together, it makes a really loud sound. So there's a lot of energy released, and then they're held really tight together. And so it's going to take energy to pull my hands apart from each other. So I've literally done that in exams where I just go like this, but not too loudly because I think everybody else will think you're a jerk. But okay, covalent bonds, these are your strongest ones. Electrons are shared, right? That's what these little sticks mean. Okay, I'm sure you all know that. Electrostatic interactions, kind of the 2 that you're going to need to know are going to be like ionic bonds, right? So in ionic bonds, electrons are transferred, right? So, like sodium chloride. For example, sodium gives away its electron, develops a positive charge. Chlorine grabs an electron, develops a negative charge. Then there's an electrostatic interaction. Salt bridges, just know it's an electrostatic interaction. I don't think she'll ask a question on it. And then the one thing you do need to know is that the energy of these bonds is inversely proportional to the distance. And then hydrogen bonds, like we've gone over many times, whichever has the bond to the oxygen is the H bond acceptor. So say I have an oxygen here. Okay, so this one's going to be the hydrogen bond acceptor. And then the one with the bond drawn to the H is the donor. Okay, so this one has a hydrogen, it's going to donate its hydrogen. Questions about that? I think there will probably be a question about that on the test. So, and then van der Waals, the key things you need to know about van der Waals is that the size of the atoms involved is proportional to the strength, right? If you have, because it's about like this electron cloud density, right? Kind of creating these instantaneous dipoles, right? And so if you don't have a very large cloud, it's not going to produce a very large charge, right? So like if we had like an electron with like 4 electrons and like 2 electrons migrate to one side, it's going to be a very weak interaction. But if I have one with like 56 electrons and 23 electrons kind of migrate to one side, it's going to be a much stronger interaction. So size and surface area are the keys in van der Waals forces. That's why our amino acids such as leucine, right, with kind of this big surface area are able to form those van der Waals or hydrophobic interactions. Questions about that? Yes.
What's important to know about the electrostatic interaction?
This. So this is the energy is inversely proportional to the distance, which makes sense. I mean, if you guys have magnets, you have a positive magnet and a negative magnet, and you hold them this far apart, there's not going to be as strong as a pull as if you hold them this far apart, right? It's kind of the same thing with electrons. Yeah. Any other questions? Okay, I'll review this table one more time. Covalence 1.5, van der Waals is 1. The others are between that. I would memorize these 3 numbers specifically, memorize all of them. But these are the ones that like to be tested on, I've found just through going Dr. Seefeld's exams and her practice exams. So memorize this. Anyone have any questions about it? Okay. Okay, and here's our functional groups, right? You all probably remember these ones from OChem, right? Alcohol, pretty easy, amine, aldehyde, ketone. If you haven't memorized them, take a picture of this, practice drawing them. It's going to be key to you. The one that you might not recognize is an organic phosphate, okay? And this one's important, especially when we talk about our nucleotides, right? And often that phosphate group is there, right? Here's like our nitrogenous base, right? And so it's important to recognize it because she might have like a picture of a nucleotide and be like, what functional molecule is this? And point to the phosphate group, right? And so it's important to know that one. And then thiols, what amino acids have thiols? A thiol functional group. Cysteine. Methionine does not. Methionine is a sulfur to a methyl group. Cysteine has that thiol group. And what can it form? Not salt bridges. Yeah, disulfide bridges, right? Good job. So that's where you'll see those ones. And it's kind of important to know where these happen. It helps you know what they are. Any questions about these? Okay. If I'm moving too fast, just tell me. But but I got a lot of questions. I'm sure you guys have a lot of questions to get through. So, all right, number 6, if the pH of the solution increases from 5 to 8, how does the concentration of protons in the solution change? F. Yeah. And why is it F? Or is just F your lucky number? Go ahead.
Because pH increases, that means increase in A plus concentration.
Exactly.
State how much it increases, put it to the 10, but 10 to that power, so 10 to the third.
Yep. So increase by 3, 10 to the third, it's 1,000. We know that we are going up the pH scale, so it's decreasing. It's decreasing by a factor of 1,000. Yes.
Just to make sure I have it right, where if it decreased by from E5, it would just be E.
Yes, exactly. Right. So if we went from pH 8 down to 5, we're increasing our proton concentration, and that causes it to be increased by a factor of 1,000. Okay. If you get stuck on this one, and maybe you get like that anxiety on your test, right? I don't know, but you can always just calculate your pH as the negative log of H plus, and you can just plug in your pHs here and solve. But that seems like a lot of work. But if you're stressed out, that might be a good way to do it. Questions? Okay. Okay, so this one's going to be calculations. Everyone pull out your pencils. There will be a couple of these on the exam, so it's good practice now. Common biological buffer is a compound known as tris, which has a pKa value of 8.07. If a buffer solution is made where the concentration of your weak acid is 0.25 molar, and the concentration of the conjugate base is 0.4 molar, what would be the resulting pH of the solution? So I'll see if we can start off with a hint. What equation are we going to use? Henderson Hasselbeck. I'll write that down for you guys. Do you guys get an equation sheet? Okay, then I'll write it down for you guys so you can use it. Yeah. So if maybe that will jumpstart you. But someone just shout it out when they have the answer. B. Okay. Of course it's B. And I'll walk through it really quick. So what we want to solve? We want to solve for pH. Now the pKa is 8.07 plus log. A minus is 0.4 divided by 0.25. This is where you're going to plug it into your calculator. And you're going to get the magic number. And that is correct. Any questions on that? You guys all know how to use log buttons on your calculator. If not, now might be a good time to figure that out. Okay. All right, similar question. pKa is 4.75. We make a buffer from acetic acid and acetate. The pH is adjusted to 4.5. What is the ratio? So I'll write this down again for you guys. So just whoever gets there first can shout it out because I'm going to go through it. Hey, yeah, good job, guys. So let's go through this. We know pH. Okay, 4.5, pKa 4.75. And we want to find this ratio. Well, actually the inverse of this ratio, but we'll get to that later. Subtract this from this side. 5. Minus over HA. You guys following me? Making sure I'm not messing up on my algebra, right? Okay, sounds good. Take 10 to both sides. 10 to the negative 0.25 is 0.562. And this will cancel. Does that make sense? Everybody understand why this cancels? Okay. Okay. And so you might think, boom, I'm done. But read the question carefully because I guarantee she'll do something like this or something similar. Okay. We want HA to A minus, not A minus to HA. So I need to flip this. Just means I have to take this and flip it as well. Make sense? Perfect. Everyone on Zoom, does that make sense? Okay.
Yeah.
Perfect. Okay, spontaneous association of the non-polar molecules in water is driven by the blank, which is facilitated by a what? Yeah, good job, guys. So someone give me the easiest definition of entropy they can give. Yeah, so decrease in order. Is that what you? Yeah, disorder, right? Chaos, right? Which makes sense. The way I think of it is if I burn a piece of paper, it's going to be very hard for that ash to go back to the paper, but it's relatively easy for that paper to go into that ash and become many parts, less ordered. Okay. And so the hydrophobic effect is, let's say that we drop a bunch of little fat particles, which are hydrophobic, in water. Okay. There's a lot of, these are kind of disrupting the hydrogen bonds of the water molecules. Like they can't really go through here, right? And it's kind of making them ordered because it's telling them where they have to be, right? Like you can be on this side or this side, but you can't be here, right? And so what the hydrophobic effect does is it coalesces all these hydrophobic molecules together. So they're in a better ordered state, right? All the hydrophobic interactions are occurring, which this makes sense, right? If you had something hydrophobic, it would make sense for it to fear the water and so form interactions with other like-minded. And now this water has a lot more ability to zoom and zip and bump into each other and make those interactions. So probably the worst explanation of entropy, but it's kind of the one that you need to know for our purposes. Literally just memorize this answer and you'll be good. Yeah.
Is like spontaneous correlate with decrease in entropy?
So spontaneous would be an increase in entropy. So we actually have so an increase in entropy means it's becoming more disordered. Yeah. So like it would be really weird if all of you guys walked in the door. This is like a psychological example, but it's a good example. And you all sat in that top corner, like right next to each other, like almost holding hands. Okay. You guys have kind of spread out a little bit, giving yourself space. Right. And so the ability to do that, like gas molecules are much more active. They have higher entropy. And so if we're able to make a gas, we do. but it's kind of confusing when it comes to the hydrophobic molecules. Just know that it allows for water to be more disordered, even if it seems like it's making the hydrophobic molecules more ordered. So memorize this answer. It's from your slide. Hydrophilic effect isn't really a thing. Yeah, this is just kind of a just kind of throwing you off, right? It might be a thing, but it's not a thing as far as we're concerned. Okay. Yeah, because I guess the hydrophilic effect would just be the inverse of the hydrophobic effect, which is polar molecules like to be together. So yeah, sorry. Any questions about that? Okay, just remember, hydrophobic effect increases entropy. Got it. And that's a good thing. Okay. I'll talk on that later. Okay. So pH key takeaways. pH is the negative log of your proton concentration. pOH is the negative log of your hydroxide ion concentrations. I find this one kind of useful because I know she has asked questions in the past where she gives you like the concentration of OH and she asks you, let's say it equals like 6 times 10 to the minus 8. And she'll ask you something like, what is the pH, right? And like, there's a way to do it where you know, like the concentration of OH times the concentration of this. It's like 1 times 10 to the minus 14, right? That's a lot of math for me. I don't like to do it that way. So I just take the negative log of this guy. And that's going to give me my pOH. And so then if I just take 14 minus that, it'll give me my pH. So that's useful to know that these two add up to 14. Any questions about that? Okay, the other example, the other one that might be good to know is KW. Okay. And this is 1 times 10 minus 14. That's what that E means. I'm sure y'all knew that, but and that's just, what is that? Do you guys remember? Yeah, it's like the auto ionization of water is what it is. And so, you know, this is literally just a equilibrium constant, right? And so it's just products over reactants, and that tends to give us that number. If you're confused about this, go back, watch our lectures. But in all honesty, it's the pH and the pOH that you need to focus on. But this would probably be a good number to know as well. Make sense? Okay. If the pH is less than 7, what is it? These are supposed to be transitions, but obviously they're not. Acidic, right? Good job. 7's neutral, above 7's basic. Okay, here's a good one. And this will tie into our amino acid talk. If the pH is less than our pK, our weak acid will be protonated. Okay. And if the pH is greater, our weak acid will be deprotonated, kind of a no-brainer. Am I getting the chats? If the concentration of weak acid and conjugate base are equal, what is the pH equal? pKa, yeah. So not 7, right? That might be this is water. I think. I don't know. I don't think so. But anyways, it's just basically, let's draw our yield titration curve. You guys all done your titrations in your biochem lab? You're all experts, right? Okay. So I'm just going to draw the first part, right? I'm going to start here. Okay, and because it's a buffer, there's a little bit of resistance here. And what's a good kind of pH range for a buffer for resistance? It's like, or like plus or minus 1, right? Basically plus or minus 1 from its pKa. Does that make sense? Yeah. So if it was a pH of 7, if it had a pKa of 7, you'd be exactly right.
Okay.
Yeah. Yeah. And so, and then this point right here. Well, let's ask this one. What's this point right here? So this is the isoelectric point, right? Right? I have not seen these charts on tests, so don't stress too much about it, but I think it might be important to understand because it helps you understand the concept better, right? And then what's this point here? This is your pKa, right? Right, so pKa, right? And so as we can see here, when the concentrations by Henderson-Hasselbalch equation, back, I don't know, probably saying it totally wrong. If these are equal, what's this concentration? Not quite. 1, then what's log of 1? 0. So our pH equals pKa. Okay. And just kind of think of this like you're rolling a ball up the hill, right? If your pH is less than the pKa, you're still rolling the ball up the hill. And so you got that extra proton. And then once you're past this point, that proton fell off and it's deprotonated. So I don't know if that analogy works. It works for me, but I think it's weird. Yeah, it does, but I'm just drawing half of it. Like on if you know, like who's in the lab? Yeah, so you guys know that like there might be like another pKa point here. It just kind of depends. And this is just a rough drawing. So this is what I want you guys to focus on. Questions on that? Okay. Okay, entropy. So like I said, we will talk about this. Hydrophobic effect increases the entropy of water. Say it with me. Hydrophobic effect increases the entropy of water. Okay. So this affects protein foldings. Why would it do that? Yeah. So the hydrophobic parts are going to want to stay inside the cell. Here's a valine. Here's an isoleucine. Here's just a plain old leucine. All right, they're going to stick out here. And then on the outside, you're going to have your polar guys like tyrosine, serine, threonine. All right, this is all going to be on the outside, right? But
I have a question about structure. What do we have to know about primary structure and secondary structure?
yeah, so you're going to want to know what bonds cause that one, right? So primary structure, for example, is peptide covalent bonds, right? And then secondary structures, you got to know what they are. So there's 3 of them. There's beta sheets, alpha helices, and turns, right? And then what holds them together? So that's hydrogen bonding on what? Nope. On the main chain, right? Okay, and then tertiary structure is between R groups, and there's many interactions between besides hydrogen bonding. We're going to go through all that, but we'll hurry so we have enough time to get there. And so these are 2 important equations. They're on your equation sheet, I believe. If not, memorize them because it's just useful information for general knowledge, right? So here's what I was talking about with the increase in entropy, right? What delta G values indicates that something is spontaneous? Negative, okay. So if we want delta G to be negative, let's say that we have heat is released. So that means that delta H is what? It's released. Negative, right? Okay. And we want to have a more negative number. Does that mean we want our delta S to be positive or negative? Positive, okay? So that's how I think of it. Increasing the entropy is going to lead to a more negative number, which is going to make it more spontaneous. Yes, exactly. Delta S is change in entropy. So that's your enthalpy, which we measure when we do experiments in release of heat, or heat put into the system, heat put out of the system. Does that make sense? Yeah. And so if you're putting heat into the system, yeah, and if heat is being put out, yeah, it's negative, exactly, right? And so a typical test question, if she asks on this one, will be something like, what values of delta H and delta S will lead to a spontaneous reaction, right? And she'll ask something like a positive delta H, or here, I'll make a table. I think she did this in class, actually, like a positive delta H and a positive delta S, a negative delta H, positive delta S, negative delta H, and negative delta S, right? And if you look at this, okay, what's a positive delta H going to make? It's a positive, right? So a positive, and then we're going to subtract. What's a positive delta S going to do? Yeah, so we're going to subtract a positive number. And we don't know what's going to happen because we need to know the size of the numbers in order for us to determine if it's going to be negative or not. So nothing can be concluded from here, okay? What about negative? So let's say that delta H is negative. So we have a negative number. And then delta S is negative. So we're subtracting a negative number. Nothing can be concluded, right? Because this is the same as adding a positive number to a negative number, and it depends on the magnitudes in order to determine what's going to go on, right? And then, you might have something like, well, if we have a negative minus another negative number, or minus a positive, which is subtracting a negative number, this is always going to lead to a greater negative number, right? Can you guys see that, or is it kind of hard? It's going to lead to a greater negative number, right? Because you have a negative thing. So let's say that this is -5. We'll put numbers to this, and we're going to subtract, let's say our temperature is 3, and then we have a positive change in entropy. So let's say that this is 5 as well. Well, this is a negative number, and we're subtracting a negative number, right? Or we're just, subtracting a negative number, right? So it's becoming more negative. So this would be like -20, right? And so practice with these ones. I don't know if she'll have a question on it, but it is good to understand. I don't know if I've seen a question like this on our quizzes, but I've seen it somewhere. Does that make sense? Okay. And then this one's on your equation sheet too. What is KEQ? Equilibrium constant, right? Good job. Okay. And then, like I was talking about, entropy is essentially just an increase in disorder, more chaos, right? Chaos is good, at least the spontaneous things. Any questions about this stuff? Okay, we're gonna move quickly then. All your guys' favorite stuff, amino acids. Which of the amino acids below would be classified as polar based on its side chain? E? Good job, everyone. So let's just draw these really quickly. It'll be good review. What does valine look like? Looks like a V. Good job. What does leucine look like? It kind of looks like a V too. but just a little bit longer V. What does alanine look like? Yep. It's the methyl group. What about isoleucine? This one's always hard. Yeah. I don't know what you mean by owl, but oh, an L.
Like straight in the line, kind of. I don't know. It's kind of like a valine, but like one of the thing larger, I guess.
I think that's leucine. Leucine, you see an L.
Well, yeah, but like they're the same size, so I think they still see that.
All right, yeah, whatever works for you. And then tyrosine, what does tyrosine look like? Looks like a tire. Good job. Yep, like a big wheelbarrow, right? And then this is a tire. Make sense? Okay. I know a couple of people joined. Do you guys have any pressing questions that you need answered right now? Okay, sounds good. All right, everybody good on this? Y'all got all your amino acids and their ionizable side chains memorized? Yeah, you do. Good job. Choose the correct name for the amino acid below. Arginine. Okay. Let's draw these side chains. So what's serine look like? What about phenylalanine? Good job. You know, it's like alanine, but with a phenyl group, right? What about aspartate?
That's the one. That's like,
Yeah, how many carbons before the carboxylic acid? It's the shorter chained one, right? What about alanine? Yeah, methyl group, right?
I always keep confusing alanine with
Glycine. What's glycine look like? Yeah, it's just an H, right? It doesn't have a side chain. You guys want to know how I memorize this one? I think if N were like pirates, this one would be saying arg because it's got a lot of nitrogen atoms. Yeah, I don't know. It's not very helpful, but I thought it was kind of funny. So any questions on these? Okay. Yeah, what's its pKa? It's like 12. Yeah. Yeah, you do need to memorize the ionizable. I missed 2 questions. First one was my worst exam, and I'll tell you guys all why. I did not memorize the amino acids, and I did not memorize the ionizable side chains. I just kind of guessed, and I still did okay. So don't stress too much about it from that lived experience, but do stress a lot about it. Okay, so any questions? Memorize them. Don't be lazy like me and just memorize them. It's just easier. Okay. Yeah. So what are they? You got histidine. What's histidine? Okay. What about the negatively charged ones? 4. What about tyrosine? Good. Yep. What about lysine? Good job. So they're all kind of in the same area. Yeah, we'll go over that later because I think it's fun to quiz you guys. Okay. Which amino acid would you predict to most likely find on the interior of a protein? Someone shout it out. Good job. Why leucine? Yep, hydrophobic. Key thing there is interior. What would be on the exterior of a protein? Polar, right? So glutamate, what does this look like? Yeah, it's negative. So it's the longer one that's got a carboxylic acid. And you're right, it normally is negatively charged. What about asparagine? Shorter what?
The one that's not, it still has this H.
It's a shorter amide, right? Okay. Serine? I've already drawn this one. Cysteine. Yeah. I forgot how many carbons are in this one. I think it's 2. Yeah. Any questions on that? Yeah. No. So this is asparagine. Leucine is that. Yes.
So glutamate is that the what is it, deprotonated form of glutamic acid?
Yeah.
Okay.
Yeah. So this is glutamate. That's a good catch there. One that we don't really go over. So this is glutamate. What is this? So this is glutamic acid, right? Because it's still got its proton. So glutamate will have that negative charge. Is this good practice, me drawing these structures? Okay. All right, which amino acids contain a thiol group? Cysteine, right? So draw this one again. Arginine, I'll refer you back to, oh, I haven't drawn arginine. What is there? So this is a thiol group. Yes, exactly. And yeah, we went over that in the functional groups. And I will send out my slides to you guys. I don't know if it'll be helpful, but you'll have them. Arginine, yes.
Okay, sorry, this is kind of earlier, but I thought when they had that big slide with like a bunch of different of the structures, I thought thiol had it was like S bonds and OH, not OH.
No, it's just an SH. I can go back.
There it is. Oh, it's just the. Okay.
Oh yeah, it's just me. I tried to like crop it and then I just screencasted it. Sorry. I just screen snipped it. Sorry. It's just an SH. Sorry. That's why you guys are like, what? You're an idiot. And I am, but it's okay. Okay. Arginine. So there's like 1, 2, 3
That's the
carbons.
the
Yeah, if N's were like pirates, this one would be saying arg.
There's 3
There's 3 people and they're all captains. I don't know how many carbons are in here, so don't quote me on this. You don't need to know how many carbons. The important thing is to recognize this. I think it's called an imidazole group. Once again, that's above the scope of this class. But just recognize this kind of conjugated and cry thing. Okay. Aspartate, done this one several times. It's got 2 carbons. Serine, what's this one look like? OH, tryptophan. Yeah, so I don't know the structure for this one. I just remember that there's a benzene ring. There's like an H here. And then there's like a 5 carbon ring. Yeah, that's probably not what it looks like, but it's the biggest one, right? Tryptophan's the biggest one. I remember that because W is near the end of the alphabet, and so it's the biggest letter of the alphabet. I don't know. That's probably a bad way to memorize it. I just say how I memorize it. Yeah, sorry. Forget what I just said. There you go. Yeah, tryptophan. It's easy to trip over because it's the biggest one. That makes sense? Okay. Oh, okay. What would be the overall charge on the amino acid tyrosine at pH 12? Shout it out when you get it. -2. See if they're right. Let's draw this out. What's tyrosine look like? Yeah, it looks like a tire, right? This is why I wasn't a OChem SI because I can't draw. So, okay. pH 12. What's the pK of this group? You're right. I don't know why I'm listening to you guys. Yeah, this is 9. Okay. What's the pKa of this of your carboxyl group? What's the pKa of tyrosine? Is this going to be protonated? Not. Yep. Exactly right. Deprotonated. So what's this charge here? This one? This one? Good job. Does that make sense? How to do that one?
NH3 plus and then CO minus.
Yeah.
C and then the chain, like tyrosine.
That's what I did. I just did it with the stick. There's an H here, right?
Oh, true. Sorry, my
Yeah.
bad. That's what it is.
Yeah, yeah. So she draws it like this.
Okay.
And this might be more helpful. But
Okay. Like, should you conclude that the charge is negative on the carboxyl group and is positive on the amino group, or do you just leave it neutral until you factor in the ether?
so I just draw them protonated. This is how I do it. It's up to you, right? I draw them protonated. I write down their pKa's, and then I go from there. Yes. Yeah, I mean, it's up to you. Yeah, like you could go like this, and then that would be +1 to 0. So
Well, this is usually have a positive factor.
yeah. When I get to like long amino acid chains, like let's see, I had histidine, valine, leucine.
You only have to worry about
Yeah, this is what I do. Tryptophan. I just do charges, right? So I say, let's say my pH is 12, deprotonated, non-ionizable, 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 deprotonated, deprotonated, non-ionizable. That's how I would do that. So, any questions about that? Yeah. We'll do more practice. Don't worry. All right. Which letter correctly identifies the psi bond in the peptide shown below? That was quick. How'd you know it was A? Yep. C, psi. It's A. This is a carbon. This is a carbon. What's B? Peptide. What's C? C is the peptide bond? Phi bond, right? Questions? Yes. D would just be, yeah, I guess it wouldn't really be labeled. Because it's not connected to anything. So it's not a peptide bond yet. This would just be, yeah, just a covalent bond would be a good answer for that one. Yes, B is peptide. what's cool about peptide bonds, they have partial double bond character, right? Which means they are, sounds like an airplane. Planer, good job. Any questions? Okay. Our Ramachandran plot shows regions of allowed combinations of what bond angles in the primary structure of a protein. Everybody agree on A? Yeah, so Ramachandran plot. Oh, I can't remember. I think this one's psi, this one's phi. Then like these quadrants, like minus 180, 180. I don't know. I'll have a better picture and you don't really need to know how to draw them. Just know what they're measuring. Makes sense. And what does that show us? Like why are there different kind of regions here? Yeah, so steric hindrance is the key, right? Right? You guys got that? Does that make sense? Okay. Any questions? Okay, what is the net charge on the tripeptide? What is ALA? What is GLU? What is LEU? At pH 7. Leucine, I believe, is non-ionizable. There's another L1. What's the other L1? Yep, lysine would be 12. Okay, anyone got an answer yet? Well, let's draw it out. So we have our NH3 group here. Whatever, we have alanine, glutamate, leucine, and then we have our COOH group. Does alanine have an ionizable side chain? What about glutamate? What's its pKa? So at a pH of 7, is it going to be protonated or deprotonated? Deprotonated. What about leucine? Does it have an ionizable side chain? What's the pKa here? 3. So is this going to be protonated? What's the pKa here? Is it going to be protonated? Okay. 1 plus 1, or 1 plus minus 1 is 0. Minus 1 is minus 1. Make sense? Any questions? Okay, so know the ionizable side chains. Amino acids are connected via a peptide bond, which releases a water molecule in its formation, right? Okay, the peptide bond is between the carboxyl terminus of one amino acid and the amino terminus of the next. pH bond is between N terminus and carbon connected to the R group. Okay, we kind of went through this. Do you guys want me to draw them? Okay, let's go back to here. So we start here with our amine group, right? And so what is this one? We have a carbon, we have a carbon. What's this bond here? And then here, what do we have? And how do you know it's peptide? Yep. So this actually has partial double bond character, right? Then what's this one? Phi. Okay. And so the way that you recognize it is C, psi. Your amide group, peptide. And then N to C would be phi. Okay. And so the way I think of it is that I'm fine to go to the next amino acid. Means that my phi bond is connecting me to the next one, right? I don't know, that's probably a bad way to think about it. But like here we have, now we're on this part of the amino acid, and so I know that it's the next one. But probably the easiest ways to do it is just by process of elimination. So CC psi, identify your peptide bond, and then the one between the nitrogen and the carbon is going to have to be the phi bond. Okay, and that accounts for all the bonds, right? Like if this were to keep going, right, this would be our phi bond, this would be our psi bond again. This would be our peptide bond. If this was keep going, right, we would have another phi bond, another psi bond, and another peptide bond, and then another phi, and it just keeps repeating, right? So if you can't remember which one's which, just memorize the ones that you can and then go by process of elimination. Is that helpful? Yeah. Let me know if I'm being redundant. Okay. Any questions about those? Okay, so I'm going to test your guys' group on the pKa's of the ionizable side chains here. What's this one? Terminal alpha carboxyl group. Yes. Okay, aspartic acid, glutamic acid, histidine, alpha amino group. Come to a consensus. 9. Cysteine, tyrosine, lysine, arginine. See if you guys are right. 3, 4, 6, 8. Well, she said 9, didn't she? Yep. 8, 10. She said 12, yeah. And then 12. Good job. So I would just do that, cover up one side, write them down, see if you guys got it right. Has anyone got questions about that?
How come she edited?
She probably did it because she does it closer to like experimental values. I don't know. That'd be a good question to ask her. This is just what she's asked you to memorize. Okay, any questions? Okay. So memorize your amino acids once again, non-polar, polar, positively charged, negatively charged. This is how I memorize them. I memorize them in groups. You guys have any question on these? Okay, I would just do this, draw them out, draw out the side chains, and see what you come up with. Yeah, so lysine's the one that has the long chain, and then like an NH3 group. Right. Any questions? Okay. Here's your Ramachandran plot. I already kind of went over this. So green means favored, and then white means non-favored. Okay. And that's all you really need to know. Did you guys watch the YouTube video? It's kind of interesting. It was good. I would watch it. I think it's interesting. Okay. Now back to the stuff. Okay. Okay, which of the choices below best describes the bonds or interactions that stabilize the protein alpha helix?
What is D the answer?
Yes, D is the answer. So let's go through these really quickly. So let's just go through this. Number one, the peptide bond is covalently bound to the COO from the peptide bond in the amino acid, 4 amino acids ahead. So what kind of structure is an alpha helix? Secondary structure. Are these stabilized by covalent bonds? No, right? What are stabilized by covalent bonds? Okay, so right off the bat, we know that this one's not the answer. The NH from one amino acid side chain forms a hydrogen bond with the COO from another amino acid side chain, 4 amino acids ahead in the chain. So let's draw this out. So we have our NH. Okay. And then we have our COO. There's 4 amino acids here. And then we have our carbonyl carbon. And so what's kind of the key thing here that's throwing you off? Side chain, right? Secondary structure has to do with side chains. Has to do with the main chain, right? So now that this one's not one. Main chain. Okay. Okay. Right here, what do we see? Side chain, right? Side chain and covalent bond, so that's a double N, right? The NH from the peptide bond forms a hydrogen bond with the COO from the peptide bond. So it's kind of hard to draw, but I'll do my best. So we have our alpha helices here, okay? And on these alpha helices, we have our groups coming off. Okay. And then what is making this alpha helice hold together is that the amine terminus has a hydrogen atom and 4 amino acids ahead on the main chain. What's the main chain? Yeah, so it's your phi, psi, peptide linkages, right? And so these are going to form hydrogen interactions about every 4 amino acids. And that's what kind of holds this whole thing together. Okay. Now, what if I had amino acids that were like this? What would this be? Data sheet, right? Is this parallel or anti-parallel? Why is that? Yeah, go in different directions, right? Which one's stronger? Oh, yeah. So what's stronger of the beta sheets? Parallel or anti-parallel? Anti-parallel, right? So this is stronger. And that's because parallel kind of form like this zigzag. And so the hydrogen bonds have to go a greater length. I don't know, can't draw today, but does that make sense? So remember, you don't even really need to know the shape of an alpha helix to know this one. You just kind of notice that it's on the main chain, right? So if you see side chains, that's not going to be it. See covalent, that's not going to be it, because the secondary structure is formed by hydrogen bonds on the main chain. Does anyone have any questions about that? if a protein, which is found to contain two identical polypeptide subunits, which of the following would be an appropriate representation of the quaternary structure? Everybody agree with her? Yeah. So why is it A? Yep, so what would this indicate? Yep, so you have one that's like this, have one like this, okay. Why not this one? Yep, start with alpha and go down the alphabet. What about this one? Yeah, so this one's wrong two ways, right? Because you're not following the alphabet and you have two different ones. Make sense? Any questions? Yes. Okay. It depends on if they're identical or not. In theory, if you had 16 polypeptides that hung out together, you'd have alpha 16. If 8 of them were one kind of polypeptide and 8 of them were another, you'd have alpha 8, beta 8. Yeah. Yeah, so the kind of the key thing here is you see the two identical. If it was two unique, what would be the answer? Make sense? Okay, key takeaways for protein structures. I've harped on this a lot, but I think it'll be a good review. Primary structure. This is the actual sequence of the amino acids. Okay. Stabilized by covalent bonds. Peptide bonds. Secondary structure. Local structuring of amino acids. Okay, so this is just local. You can have like an alpha helice, have a turn, have a beta sheet. You can have another beta sheet connected by a turn going into another alpha helice. Okay, the key here is we're just looking at certain regions. So it's like you were to build a mansion with Legos and you needed to build a bunch of doors. Those would be secondary structures. Make sense? Okay, so these are stabilized by hydrogen bonds between the carbonyl, oxygen, and nitrogen on the main chain. Okay, it's got to be on the main chain. Can't be side R groups, right? I don't know how important these numbers will be, but I know that they can be important. So I know this one's important. It's 4 ahead, right? So going back to this question, it 4 amino acids ahead in the chain, it forms that hydrogen bond. And so because of that, it's pretty close to 4 amino acids per one turn, but not quite because you're only going part way through the chain. Does that make sense? Right? Because like, you know, the whole chain is N, R group, right? And keep going on. And then you're just binding to the first part. So it's about 3.6 long. So, and then the pitch is about 5.4 angstroms. I would suggest memorizing these numbers. I don't know how important they're going to be, but I've seen them on quizzes and stuff in the past. Beta sheets bind with adjacent chains. Anti-parallels more stable, can form beta barrels, and that's just like basically just like a bunch of beta sheets. It's hard to draw in 3D, right? But like a bunch of beta sheets. Like that, right? It forms like a beta barrel. And then it's like hollow in the middle, right? So like a protein channel. Turns and loops are often hydrophilic on the outside of a protein, right? That makes sense. So this is a turn. Yes.
I'm wondering about like fish, it's like turning slightly again. Why was that?
So I'm gonna be honest, I'm not exactly sure on the reason why. I don't think it's very high yield for this exam. But as far as like just your curiosity, I would think that it would be because the R groups, there's some steric strain there because you know they're binding between these two, right? And if there's R groups that like to be on opposite sides of each other, maybe that just creates some torque, you know, and that torque will kind of bend it. So that's my best guess, but I don't know. Tertiary structure is your overall 3D structure, and this can have pretty much any interaction you can think of. Ion, ion dipole, 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 hydrogen bonding, van der Waals, covalent bonding, rarely. And then the interior is typically nonpolar. And why is that? Yeah, so hydrophobic effect, right? Exactly. Quaternary is how two or more polypeptides interact with each other. Subunits can be same or different. Kind of went over that. Any questions about that? Yes. Yes. And so that's one of the few covalent linkages. And so can you have covalent linkages in quaternary structures? Yes, but it's very rare, right?
Picture with quaternary, that's like, those, like, beta.
Yeah. Yeah, that's the only time. Okay, any questions about that? Okay. Oh, here we go. If the value for Gibbs free energy for reaction is negative, the reaction is what? Yeah. So why would it not be exothermic? Yeah. So what's the word for spontaneous? Exergonic? Yeah, good job. And then endergonic is non-spontaneous. Taking in total energy, endergonic, putting out total energy, exergonic. Questions? So what would an exothermic reaction have?
I know it's like taking energy.
Yeah.
from the sun.
So that has to do with delta H.
Okay,
So an exothermic would have a negative delta H. And then an endothermic would have a positive delta H. Okay, you had a question.
Yeah, could you just say that again? If you were down once, out.
Yeah, so exergonics spontaneous, it's putting out total energy. Endergonics non-spontaneous, which means it's taking up energy. Questions about that? I'm going to start hauling, guys, because I feel like I've wasted time. Enzymes accelerate the rate of a chemical reaction by what? Yeah. Another way you could say that is stabilizing what? Yeah. Okay. Questions about that? Okay, which of the following would be acceptable units for the value of Km for an enzyme? B? E. So Km is what? Yeah, so it's the amount of substrate needed to reach 1/2 Vmax. Does this depend on enzyme concentration? It is a 50-50 chance. No, it does not. So yes, right? And so here we have the concentration of our substrate. And here's our V naught. If we had just one enzyme, like 1 molar enzyme, we'd have something like this. We had 2 molar enzyme, reach pretty much twice the Vmax. The thing that would not change, and I'm a terrible artist, so you'll see a better picture of this, is Km, because it's an intrinsic property, and that's the amount needed to reach 1/2 the Vmax. And Vmax is dependent on substrate concentration. Or, I mean, enzyme concentration. Makes sense? Vmax. And that's enzyme concentration. It's also affected by substrate concentration, but the important thing is enzyme. Okay. Any questions? For an enzyme catalyzer reaction, the value of Km is found to be 2.5 micromolar Vmax is 22 micromolar product per minute at a substrate concentration of 1.4 micromolar. What would be the expected rate of the reaction? Do you guys have Michaelis-Menten equation memorized? Oh, wow, there you go. You don't even need it.
Is the registry on campus?
I would assume so. It's been a year since I've taken it. Yeah, I think it's on the front page of our Canvas page. Yeah, so for those who didn't hear it, reference sheets all the way down to the bottom of the home page on Canvas. This one's a plug and chug. B, okay. Do they have the double reciprocal equation on there? Is it like the 1 over V? No. It's not on there? Okay. Well, just figure out how to get there from here. Basically all you need to know that for is like your Lineweaver-Burke plots. You know, yeah. Oh, you'll use it lots. Just kidding.
I can see how it's useful, so I don't.
Yeah, it's very useful, especially when they didn't have computers, but we'll go over that when we get to inhibitors, but I guess I'll go over that really quick. What is this point right here? So this is minus 1 over Km, right? And then what's this one? So this is 1 over V max. Yep. And what's the slope? Km over V max, right? Make sense? Okay. Okay. A lot of stuff on here. We've already gone over this equation a bunch. I don't think I'll go over it anymore. Enzymes work by stabilizing the transition state. Why is the induced fit model better versus the lock and key model? Yeah. And the other thing to notice is that, so for a lock and key model, you'd have something like this, okay? You'd go down to this more stable state, but then you have to go all the way back up to the transition state before you got to products. And so this is a much higher delta G, double dagger, okay? Whereas the induced fit model is something like this, okay? And so it's kind of like going over 2 small hills versus 1 big hill. Exergonic versus energonic, we talked about that. Do enzymes change equilibrium? No, they do not. You guys got that equation. Kcat is Vmax over the concentration of enzyme. And then this is basically just like the turnover number, okay? When you see Kcat, think of turnover number. If I'm an enzyme, how fast can I turn over my products, okay? So it's the ability of one enzyme to convert one substrate to products. And its units are 1 over time, right? So like 1 over seconds, 1 over minutes, 1 over days, whatever. Specific activity is pretty similar. It's product formed per time per milligram of enzyme, right? So basically kind of Kcat over, it's literally just Kcat over your milligrams of enzyme, right? And so that's if like you're looking at a specific system where you put that much enzyme. I don't expect that many questions about that, but it'd be good to know. Km, we've talked about. Independent of enzyme concentration is a big important thing. Catalytic efficiency, this is your turnover number divided by Km. And so this is 1 over seconds times concentration. Make sense? Yes.
Enzymes do not change equilibrium, that means it will change the solution.
Yeah, so if you remember right, we have E plus S. So our enzyme substrate complex goes to products. So this is an equilibrium, okay? And what they're actually measuring when they measure this is just the initial rate. So right? If you guys remember this picture, this is what they're measuring. Okay, because you can have some substrate and you can have some reaction speed, but we're just worried about that initial velocity. Okay, that's what they're measuring because that determines the speed of the enzyme. Because you can have an enzyme that speeds up a concentration, but it might not make it, like, it cannot make a non-spontaneous reaction spontaneous, right? So it might be able to, we're going up this hill here. It might be able to make this hill a little bit smaller, but we're always going to have more products than we do reactants. Yes.
So regarding that graph, is it kind of like V naught is like, you can kind of get the point like when V naught's like our initial condition?
Yeah, that would be your instantaneous velocity. So that would be if you guys done rate laws, like dv dt equals minus k or minus k squared, something like that. Yeah. You taking differential equations? Yeah, so yeah, exactly like that. Okay, any questions? So here's a good illustration of Km, much better than mine. Here's a good illustration of the Lineweaver-Burke plot. Okay. Any questions about that? Okay. Hey guys, I'm sorry. We're gonna go really fast. I know it's going long, but you're studying an enzyme in a laboratory. Upon addition of an inhibitor, you notice that the value of Km stays the same, while the Vmax, the enzyme decreases. What type of inhibition is demonstrated? B. Why is that? Lower Vmax? Yep, so Km stays the same, decrease Vmax. Yeah, any questions about that?
It's more intrinsic to the enzyme substrate, or is it just the react?
It's intrinsic to the enzyme, but it can be changed by an inhibitor. Okay, so remember with a competitive inhibitor, you can add enough substrate to get back up to that Vmax, right? But the difference is because there's less available. Okay, so let's say this is your original reaction. Here's your Km. Because there's less available, it's going to take longer to get to that Vmax. Okay, and so this Km is going to increase because you have to add more substrate to get to your original Vmax. That's competitive, yeah. Then non-competitive, right? Where are we binding? Somewhere besides the active site, right? And so it doesn't matter how much substrate we add because, there's only so much that our enzyme can turn over, right? And so no matter what you add, no matter how much substrate you add, there's still going to be a percentage of it bound up, allosterically bound up, right? And so it won't be able to participate. So you can add as much as you want, but it will never be at Vmax. That makes sense? Okay. Okay, hemoglobin contains the tightly bound iron-containing protoporphyrin. Yeah, protoporphyrin. Heme would best be classified as a prosthetic. Okay, and what kind of gave that away? Yeah. If it was not tightly bound, what could we call it? Co-substrate. Yeah, perfect. Any questions about that?
So percentage rich is like, it's like as important as another polypeptide to not polypeptide.
Yeah, so like heme's that good example.
Yeah, it's even like, it's not a polypeptide, but
Yeah. Okay, and so this is a bad drawing of heme, but if you did not have this tightly bound, like if it was able to kind of come and go, it wouldn't be very good at carrying oxygen. So it's the ability of that to bind tightly that makes it such a good oxygen binder. Any questions? Okay, we're gonna get through this, guys. Enzyme activity is often regulated via phosphorylation. Which amino acid residue would you expect to be a site of phosphorylation in a protein? Why D? Yep, right. And so you can have there's a double bond, right? Can't remember. Right, this can come in here as a nucleophile, kind of switch that out. So yeah. And all the other ones are non-polar, right? Okay. Questions about that? Yeah, so typically we use ATP or GTP. Yeah. Okay, two enzymes catalyze the same reaction. The enzymes are located in different cell types in the body, have different values of Km, and are regulated via different mechanisms. These two enzymes would be an example of, and why is that? Yeah, they're isozymes, right? Right, so they catalyze the same reaction, but they're in different cell types and they have different Km values, right? So they do the same reaction, they just do it differently. Questions about that? Yeah. So what would allosteric regulation do? So that's kind of like a non-competitive inhibition, right? So that would be like, here's our enzyme, right? It's got this active site, and then we allosterically bind something to it. And so that's going to change the way that it interacts with its substrate. Okay, so it doesn't necessarily have to be an inhibitor. What's the allosteric regulator we talked about in class for like 15 slides? So that's an enzyme, but we talked about heme, right? So what does heme do? Yeah, so it exhibits cooperative binding, right? Which means that the more oxygens are bound to it, the higher the affinity, okay? So you have this heme group sitting here, or hemoglobin, I guess, technically, right? And they're just kind of chilling. They don't really, they like oxygen, but they don't want them too much. They're kind of playing hard to get. And then this oxygen comes in, okay, and hooks up with one of its friends over here. And that makes all these other hemes jealous. And so they're like, oh, I'm going to get an oxygen, right? And then this guy comes over and, they don't want to be the last ones, right? They don't want to go home by themselves. And so more oxygen are going to come until everybody's got a friend to play with that night. So yeah, the reverse is also true. Once the less the oxygen is bound, the less it wants to bind oxygen. So yeah, it's like, if no one's hooking up, you don't feel as bad about yourself. But if all your friends are, you got something to do. So covalent reversible regulation. What would be an example of this one? Yeah, phosphorylation, right? So phosphorylation, adenylation, acetylation. So basically, if you're taking like a phosphate group, a methylation, acetylation, you're adding some group to it, and it can either like activate it or inhibit it, kind of like we talked about with those phosphates groups, right? You can add a phosphate, like you add it to serine, maybe that activates it. Non-covalent reversible regulation would be an example of this one. What was that? Yeah, ibuprofen, right? So this is an inhibitor of what? Cyclooxygenase, COX, right? And so it will make hydrogen bonds with it, right? So it's not covalent, but it deactivates it, which makes it so that it doesn't produce prostaglandins and therefore inflammation, right? Questions about that?
Wait, what is the C?
It's like cyclooxygenase. I don't know. Let me look it up. It's a big long name.
I mean,
Ibuprofen. How does ibuprofen? What is COX? Cyclooxygenase. I was right. Yeah, nailed it. Okay. And then regulation via proteolysis. What is proteo?
oh, the cleavage.
Yeah, so it's protein and the lysis means to cleave, right? So cleave the protein. So yeah, so actually insulin's one of the most like interesting examples because you have like it's called like a super protein or something. When it's translated, it can be cleaved into like 6 different enzymes. And so proinsulin becomes insulin and then it becomes active. Any question about that? Okay, was that helpful? Okay. I would just go over the examples that she gives in class, especially heme. Heme is which one? Allosteric, yeah, exactly. Okay, sorry, I'm just trying to get through all the questions. What would be the correct name for the molecule below? And why is it A?
One phosphate.
Okay,
Here it's ribose, not.
yep. Yep,
I mean, yes.
so it seems like you guys got it. So short name, big molecule, big name, short molecule. What is guanine? Okay, that's a purine, so we're gonna say no. Why is it not cytosine? Yeah. So it's bound to this phosphate, right? So we know it's not going to be that one. Deoxys, we can kind of just cross these off. Do you guys have your nitrogenous bases memorized? Okay. Yeah, I don't. Yeah, that's what I was about to say. I don't think she wants you to memorize them. She's just going to want you to differentiate between pyrimidines and purines. So what are the purines? Adenosine and guanine. And pyrimidines, what are they? Which are cytosine, uracil, thymidine. Thymidine. Oh yeah, thymine. Sorry, thymine. Yeah, you're exactly right. And so if you guys were to see this bind to something else, what would it be binding to? Yes, but which one? So C binds to G, exactly. Yep. And then A binds to what? Yep. What does it bind to in RNA? Okay, any questions about that? So remember the cytidine, right? It's because it's bound to that phosphate. If it wasn't bound to the phosphate, what would it be called? Cytosine. Okay. Okay, any questions? Okay, which of the following is an incorrect statement regarding base pairing in the Watson-Crick double helical DNA? F? Why is it F? Why are they wrong? So let's go through these. So we know that A binds to T. We know that C binds to G. Okay, so these all check out. Okay. 2 hydrogen bonds between residues of adenine and thymine. So I'll tell you guys how I remember it. Has anyone had experience with PCR? Okay, so with PCR, you need a high concentration of cytosine and guanine. Why is that? Yeah, which means they have more hydrogen bonds, right? And so cytosine and guanine are hard to break apart. And so they have these 3 hydrogen bonds between them. So that's why they use them in PCR and a bunch of other things, right? And then adenine and thymine only have 2 hydrogen bonds. Okay, so we check these 2 hydrogen bonds. That checks out. These 3 hydrogen bonds, that checks out. And then these 2 are just the reverse. And so we know it's F. Yeah, so RNA is typically not double-stranded, right? And uracil is very similar to which? Thymine, right? Its only difference is basically a methyl group, right? And so I think it would be fun for you guys to memorize the nitrogenous bases. I think it would be good for you guys. But that's the important thing to know. G and C or 3 bonds. That's why we use them in PCR because they hold together very well. And then A and T only form 2. A and T, there's a T in this bond, and 2 starts with T. So there you go. Yeah, there you go. C3PO, A, C3, I don't know. Just memorize it. Any questions about that? Okay, in the formation of an oligonucleotide from mononucleotides, a blank bond is formed between the blank carbon on the first nucleotide and the 5' carbon of the next nucleotide. D. So what does a phosphodiester linkage look like? Okay. This is what we're looking at here. Are these the double bonds? Can't remember. Okay. So, yeah, these are oxygens. I just can't spell. So as you can see here, right? How do we number this? Where do we start? Yeah, so this would be 5, 4, 3, 2, 1. Okay. And we'll get into why we number them that way later in the semester. But just know that it's the 5' to 3'. You guys have all heard that in your biology classes, right? Okay, that's the directionality of DNA. Goes from 5' to 3', and it just goes to like P to the ring to another P to another ring. Jeez Louise. Right. And so it's a phosphodiester linkage, diester, because yep, 2 oxygens, diester linkage. And then that's the 3' carbon. So excuse my terrible drawing skills. Does anyone have quick questions about this? Just remember 5' to 3' phosphodiester linkage. Okay. Okay, what types of bonds, interactions contribute to the stability of nucleic acid primary structure? B. So what is a primary structure? So so we're talking about nucleic acid here. Yeah. Yeah, so this is the actual sequence, right? Right, and so the actual sequence, that's your primary structure. which follows, because that's the primary structure of polypeptides. So does that make sense? Okay. You see ionic bonds, DNA. About hydrogen bonding, where do we see that? Okay. So that would be secondary, right? Then van der Waals interaction, also secondary. And what are those van der Waals interactions? Yeah, pi bond stacking, right? An example of nucleic acid. I'm sorry, this stuff is all new, isn't it, to you guys?
Yeah.
You learned it today? Okay. An example of nucleic acid quaternary structure would be what? E. Is that what you said? So why is it E? Yeah, so it's like how it interacts with proteins is how I think about it. So proteins, quaternary structure for proteins is how proteins interact with other proteins. Well, polypeptides interact with polypeptides. So I just think analogously, it's how DNA interacts with proteins, right? So let's go through it really quick. What is primary structure, DNA? Yeah, so there's the actual sequence and it's made by 5' to 3', what linkages? Okay. Secondary structure is what? The hydrogen bonds between what? So the nitrogenous bases, right? Yeah, they're bases, right? And what else? Yeah. So the pi bond stacking via the van der Waals interactions. Okay. Tertiary structure is what? So supercoiling, right? How the actual strand coils up on itself, right? So chromatin condensing, that kind of thing. And then quaternary is how it interacts with proteins. What are those proteins called? Yeah. Did she have you memorize how many of them there are? Okay, sounds good. Okay, last one, and then I'll go through. Maybe I'm out of time. Okay. During the condensation of mononucleotides form an oligonucleotide, a molecule of what is lost? Yep, so that's kind of the key thing there. Anytime there's a peptide bond or a phosphodiester bond made, you're losing a water molecule. So that one's kind of analogous to proteins, so it's pretty easy to remember. Okay. Any questions about that? And it would not be a PO4, right? Because this is a what group? Phosphate group, right? This is glucose, and this is like a bicarbonate ion, something like that. Okay. Yeah. Yeah, so a phosphodiester linkage. Yeah. Those both release water. I have like 10 slides of review. I will go through it super quickly because I know it's late. You guys have been really good at staying with me. So competitive inhibitors, ignore this one. You guys don't need to know this one. You just need to know these two. Okay. So increases Km. We look at competitive and notice 1 over Vmax stays the same, right? So competitive Vmax does not change. Does not change, okay? But the slope does. That's because the slope is what? Because it's Km over Vmax, right? So if our Vmax is staying the same, but our Km is increasing, we're going to get a steeper slope. Does that make sense? Are you guys visualizing why we have these plots now? Yeah, okay. And so going to non-competitive inhibitors, we're decreasing Vmax. So this is kind of counterintuitive. If I decrease Vmax, what does that do to 1 over Vmax? Increases it, right? So think about it this way. If I go from 2 to 1, 1/2 is less than 1 over 1, right? And so you can see here, okay, my Vmax, my 1 over Vmax has increased, right? And that's also going to change my slope, right? Because it's going to make it a larger Vmax. or I mean a smaller Vmax, which is also going to lead to an increased slope. So, but the key thing you're going to recognize is the 1 over Vmax has increased, right? Because non-competitives do what to Vmax? Yeah. The way I like to think about it is if I'm a competitive guy, I like to be competitive and I really want to bind those enzymes, I'm going to increase my Km, okay? Because I'm going to be the most competitive inhibitor out there or enzyme out there, okay? However you want to think about it. If I'm not competitive, I'm kind of lazy, right? I'm not going to move very fast. I'm going to kind of slow down because I'm not really competitive. I don't want to play the game. And so I'm going to decrease my Vmax. Make sense? I kind of went through these. Does anyone have any questions on this? Yeah, so non-competitive. So non-competitive, our Vmax is going to change, right? So here's normal. And then here's not normal. The key here is that Km stays the same. And so thinking about this from our perspective, where non-competitive doesn't bind to the active site, but it binds to an allosteric site, right? It means that no matter how much substrate you add, there's always going to be a fraction of that that's bound up and not able to turn those into products. And so that's why there's going to be this discrepancy here. Yeah, so competitive, we can overcome by adding more substrate, right? Because competitive binds to the active site, right? But if we just increase the amount of substrate we have, eventually that ratio of like our substrates to the guys also vying for the active site, it's going to be insignificant, right? And so we're just going to kind of slowly but surely come up to Vmax. And so you can see here that my Km has increased. Yeah. Yep. Okay. So covalent catalysis, I'll go over this really quickly. Chymotrypsin does what? It cleaves peptide bonds where? After large polar R groups, right? Okay. I don't suspect there will be that many questions on this one, but I think there might be. Yeah. So it's large polar bonds. Let me make sure that's right. It cleaves peptide bonds immediately following large polar bonds. So a good example would be what? Tyrosine. Okay, sometimes serine, not that often. Let me see if she's got good examples here. Yeah, so the example she uses would be, so it's large, it's large aromatic. Large aromatic hydrophobic amino acids. Sorry about that. Large aromatic hydrophobic amino acids. So phenylalanine, tyrosine is still a good example, right? Because it's considered nonpolar since it has a very high pKa. Tryptophan would be a good example. So large, nonpolar, aromatic amino acids. Okay. And so the way that it does this is there's a couple ways to do this. There's covalent catalysis, that's temporary covalent modification. So if you remember with chymotrypsin, it kind of makes that like that kind of almost like ester linkage. Like this is like an O something. Chymotrypsin uses that. General acid base catalysis. So this doesn't have to do with the pH of the solution. This has to do with like a side group donating a proton. Metal ion catalysts. Metals are always good for accepting and giving electrons away because they kind of are like a sea of electrons. An approximation orientation. This is probably the biggest one. If you guys remember here, like these are your active side groups here, and they're far away. but when they come together, they kind of form this hydrophobic pocket. Okay, and that allows for chymotrypsin to be active. Okay, just memorize these. We're running out of time, but one thing to know is that chymotrypsin is pH dependent, right? Not pH independent. Key features of chymotrypsin are your hydrophobic pocket, catalytic triad, which is serine, arginine, and does anyone remember the last one? Yeah, so it's actually serine, histidine, and aspartate. Okay, and then your anion hole. I don't think this is very high yield, so I won't go over very much, but I suggest that you memorize this. It's pH dependent, functions at a better pH. So if it functions at a better pH, it makes sense that it'll have a greater Km value at those pHs. I already talked about this. The more oxygen is bound to hemoglobin, the more it wants to bind oxygen, right? Yes. The R state, very high affinity for oxygen. T state, very low affinity. Make sense? Okay. Isozymes. So these are examples of enzymes that do the same thing, but they function in different cells at different pHs, and they're slightly different. Okay, but they catalyze the same reaction. So the example she talked about was like fetal hemoglobin and like glucokinase versus hexokinase, right? Review those examples. Burstable covalent modification, phosphorylation, adenylation, acylation. We talked about that a little bit. Does anyone have any questions on those? Proteolysis, cutting a peptide to make it active. Oh man, I have a lot to go through. I'm just going to suggest that you guys watch the rest of. Yeah, so rewatch her lectures on DNA since that's what we covered the least. I'm going to post this on Canvas so you guys can kind of go through my notes in the last couple slides, but I want to make sure that I have, well, 2 minutes for questions. Anything anyone wants me to go over super bad. Okay, feel free to stick around if you have questions. Sorry, it was a lot of information, but I hope you guys found this useful. So. Yep, no problem. Anyone on
Thank
Zoom,
you.
if you have questions, just throw them in the chat or shout at me. I'm just going to stop the recording now.